Welcome, I am Girish Belkar and today we are continuing with the circle which we have discussed in earlier module. We have learned that the angles subtended by equal chords at the center are equal and equal chord subtends equal angle at the center. Now, let us move forward and see what happens if we drop a perpendicular from the center to a chord. So, in the figure you can see that AB is a chord and we draw a perpendicular OE from the center O of the circle. Let us observe the relationship between B and AE. Will they be equal even if I change the length AB? So, let us try and do that. So, it does not make a difference when we make AB bigger or smaller, the length B and AE always remains same. We need to give proof for this statement. So, we have a circle with center at O and a chord AB. We draw a perpendicular OD from O to the chord AB. Join OA and OB. In triangle AOD and BOD, which are right angle triangle, we have AO is equal to BO, both are radii of the circle, and OD is a common side, therefore, both side triangle have same side OD. So, therefore, triangles are congruent. So, we have triangle AOD is congruent to triangle BOD. Therefore, we have AD is equal to BD by CP/CT. So, we have proved the theorem that perpendicular drawn from center to the chord bisects the chord. Now, what about the converse of this theorem? Does the line joining the midpoint of chord to the center is perpendicular to the chord? Let us verify. So, in this circle, PQ is a chord of the circle, O is the center and R is the midpoint of the chord. Let us see what happens when we take this point towards R. So, as soon as it reaches to the midpoint, the angle between the line and the chord become 90 degree. Hence, we can say that the line joining the midpoint of the chord to the center is perpendicular to the chord. So, let us prove it. We need to prove that OD is perpendicular to AB. Join AO and OB. Now, in triangle AOD and BOD, these are no longer right angle triangles. AO is equal to BO, which are radii of the circle, OD is equal to OD, which is common side, and AD is equal to BD because D is midpoint of AB. So, therefore, all three sides of triangle AOD is equal to the three sides of triangle BOD. Therefore, by SAS congruency rule, triangle AOD and triangle BOD are congruent. Therefore, angle ADO is equal to angle BDO, but angle ADO plus angle BDO is 180 degree because AB is a straight line, and combining these two facts that angle ADO is equal to angle BDO and their sum is 180 degree, we get both are equal to 90 degree. So, hence we have proved that OD is perpendicular to AB. Let us move to another interesting fact. Millions of potholes, also called manholes, are scattered throughout the world, giving worker access to underground sewer lines. These potholes and the large hunk of metal that cover them are almost always round. A pothole cover is a circular shape. Why? A circle is one of only two basic two-dimensional geometric figures that cannot fit through an identical figure in 3 dimension. That is, if two identical circles are placed in 3-dimensional space, one would not be made to pass through another circle, no matter how the circles were angled. A square, for example, can be rotated upward until vertical to fit diagonally through a copy of itself, because the diagonal of a square is longer than any of its sides. The fact that a circle will not slip through an identical circle, ensure that having round path hole covers do not fall through the openings of the path hole and injures the workers below. However, most path hole covers are chosen to be round or circle because they have no corners. A circular path hole cover saves the energy of workers by allowing them to roll the heavy covers out of the way. So, you can see how circles are used in daily life. Let us move towards chords and their distances from the center. So, first we define distance of a point from a line. In the figure, so the length of this perpendicular CD is defined as the distance of C from the line EF. Let us explore the relationship between the equal chords of a circle and their distances from the center. In this circle, you can see there are two chords AB and CD. Both have equal length 6.18, and you can see that their distances from the centers are also 2.35. Let us now change length of AB. Length of chord CD is also changing so as to have both lengths equal, and you can observe that the length of their distances from the centers are also equal. Let us change the position of chord CD. Observe that even if I change the position of chord CD, the distance from the center of both chord AB and CD remains same. So, two chords of circles of same length are at same distance from the center. But if we have two chords of equal length in two congruent circles, will they be at the same distance from the center? Let us verify. These two circles are congruent. Let us change AB and CD. Now, both chords are of length 7.12. Their distances from the centers are also same 1.24. So, equal chords of a circle are equidistant from the center, or equal chords of congruent circles are equidistant from their centers. Now, will the chords which are equidistant from the center will be equal? Let us verify this fact also. So, here we have two chords AB and CD. The lengths are different and the distances from the center also different. Let us try and make this OF equal to OE, and let us see what happens to the chord CD. So, you can see that now the length of both OF and OE are 2.6. The chord AB and CD are also equal. Let us try one more time. Now, this time the distance OE is 2.2 and distance OF is 2.6. Let us make the distance OF as 2.2. So, as soon as OF becomes 2.2, you see that the length of chord CD also becomes 6.25. So, you can say that chords equidistant from the centers are also equal. Now, move to angle subtended by an arc of a circle. So, what is the relation between arcs and the chords? There are two arcs AB and CD, and their corresponding chords are also AB and CD. So, if we change CD, you can see that both the chord and the arc lengths are same. Now, let us change the length of arc AB. So, length of arc AB is equal to length of arc CD. Therefore, length of chord AB is also length of chord CD. So, result, if two chords of a circle are equal, then their corresponding arcs are all congruent, and conversely, if two arcs are congruent, then their corresponding chords are also equal. Result 2, congruent arc of a circle subtend equal angles at the center. This result 2 is very much clear because we already proved that equal chords subtends equal angle at the center, and equal chords and equal arcs are same. So, now study relationship between the angle subtended by an arc at the center and at a point on a circle. So, in this circle we have PQ an arc, O is the center, angle POQ is the angle subtended by the arc, at the center O, and angle PAQ is the angle subtended by arc PQ at any other point on the circle. Let us move point A. Right now what you can see that angle PAQ is half of angle POQ. And even if we increase the angle, the relationship remains same. So, at any position the relationship remains same, that is angle PAQ is always half of angle POQ. So, we have a result here. The angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Again we will prove this. So, we will take two cases. Case 1, when the angle subtended by an arc at the center is a angle less than 180 degree. Case 2, when it is more than 180 degree. Case 1, we have an arc PQ subtends an angle POQ at the center and PAQ at another point on the circle. Join AO and extend it towards B. Now, by exterior angle property, angle BOQ is equal to angle OAQ, this angle, and angle AQO, this angle. So, angle BOQ, which is this angle, is equal to sum of this angle and sum of this angle. Also, in triangle OAQ, the same triangle, AO and OQ are equal because they are radii of the same circle, and hence angle OAQ, that means this angle, is equal to angle OQA, that is this angle, because in a triangle angle opposite to equal sides are equal. Therefore, angle BOQ is equal to twice angle AOQ. This we obtained by changing OQO in this equality by OAQ. So, OAQ plus OAQ become twice OAQ, that is this angle BOQ is twice of this angle. Similarly, we can prove that angle BOP, that is this angle, is twice of angle OAP, that is this angle. Now, adding these two, angle BOQ and angle BOP, what we get? Twice of angle OAP plus twice of angle OAQ. Now, what is angle BOP plus BOQ? BOP is this angle, BOQ is this angle. So, adding them we get angle POQ. Similarly, adding angle OAP, that is this angle, and OAQ, we get angle PAQ. So, therefore, we have angle POQ is twice of angle PAQ. Hence, we have proved the result. Case 2. In this case, the angle POQ is greater than 180 degree. That means, arc PQ is a major arc this time, and A is a point on the minor arc PQ. So, same will join AO and extend it toward B. So, by exterior angle property, angle BOQ is equal to angle OAQ plus angle AQO. Again, in triangle AOQ, AO is equal to OQ, AO is equal to OQ, both are radii of the circle. Therefore, this angle, angle OAQ, would be equal to angle OQO. Therefore, angle BOQ is twice of angle AOQ. Similarly, angle BOP is twice of angle OAP. Therefore, BOP plus BOQ is equal to twice OAP plus OAQ. Hence, in this case also we have reflex angle POQ is equal to twice angle PAQ. Now, you must be wondering why reflex angle POQ, because the major arc PQ subtend and reflex angle at the center. Therefore, we have taken reflex angle POQ. Hence, we have proved this in second case as well. Next, angles in the same segment. Let us see what is the relation between these two. PQ is the minor arc and C and A are on the major arc side, and you can see that both the angles are equal. Let us change. So, even if I change the position of Q, you can see that the angles always remains same. Let us change the position of C. This angle remains same. Even if we move P, then also there is no change in the relationship. So, we can conclude that angles in the same segments are equal. Now, the question is converse also true? That means, if the angles are equal, then will these 4 points will lie on the same circle? Let us verify. So, here 2 points CD on the same side of the line segment AB, they subtend same angle. Let us draw a circle through A, B and C. So, you can see that the circle also passes through D. Let us try one more time. Now, this time line segment AB subtends angle 50 degree on point C and point D. Again we draw a circle, the circle passes through all 4 points, and such points we call them concyclic points. So, if a line segment joining 2 points subtends equal angles at 2 other points lying on the same side of the line containing the line segment, then the 4 points lie on a circle. Now, the question comes, why study these properties? What is the use? Does it help us in real life? Let us see. Assume that AB is a stage. You have to choose between 2 sitting arrangements. One is the circular one as shown here, the other one is a straight line. So, chairs are in this arrangement are put in a circle, whereas the chairs in this arrangement are put along a straight line. Which one will you prefer? Obviously, we will think that since the angle subtended by AB at the line is bigger than the angle subtended by AB at the circular arc, I will prefer the seats on straight line. But see, the angle for each seat is different if we arrange them in a horizontal line, and therefore, different person will have different viewing angle for the stage. That means, the person sitting at the center will have too wide angle to see the complete stage, wherein the person at the corner will have very smaller angle. But in case if the sitting arrangement is made semicircular, you can see that everybody sitting here will have same view of the stage, and that is precise the reason why stadiums and big auditoriums, the sitting arrangements are always in a circular fashion. That is all for today. We have seen that geometry is not an isolated branch of mathematics. That means, it is not just that we learn mathematics on pen and paper. It does have real life application. There are so many applications of geometry in real life. You try to figure out, and when you do that, you will find that geometry is not a boring or a dull subject, but a very interesting one. Thank you very much.